Hello everyone, my name is Eulalia Gambera and I'm a PhD student at the University of Catania. Today I would like to present my work titled Analysis of Central Events in Nickel plus Calcium Reaction at the 35 MeV for nucleon. The 58 nickel plus 14 calcium collision was studied as a part of the thermo experiment conducted at INFN LNS in Catania. The aim of this work is to investigate the multifragmentation process in central collisions, and for this purpose I analyzed the experimental data collected during the experiment. To interpret the results, I performed a simulation using the well-known blob model Boltzmann-Langevin one-body. Finally, I carry out a comparison between experimental data and theoretical predictions. Multifragmentation occurs in central collision with small impact parameters. It is a simultaneous process during which the nuclear system reaction very low density about 1/3 on the saturation density and produce fragments with charge ranging from 3 up to 40. This is a one-step process, at the end of which the fragments undergo secondary decay of further the excitation phase. In analogy with the van der Waals equation, also in nuclear system one can speak of phase transition and therefore of an equation of state for nuclear matter. In particular, during the multifragmentation stage, nuclear matter enters a region known as a spinodal zone. Moving on the data analysis, it's essential to introduce the chimera detector, which was used for the experiment. Chimera is a 5-pi detector with high granularity, good spatial resolutions, and low energy detection thresholds. The first step in the analysis was the selection of complete events. After several studies, total charge particle multiplicity (NC) was chosen as the global variable for selecting central events. It was observed for NC greater than 15 central events are selected. This is evident from the populated central area in the Dalits plot shown in the bottom right, as well as the distribution of the three largest fragments which are close to each other in size. Regarding simulation, the blob model was used to simulate the events. The following analysis was conducted using two data sets. The first set has a AC stiffness parameter of 1 corresponding to linear behavior, while the second set has a AC stiffness of 2 which refer to a soft behavior. The results were compared both with the data produced exclusively using Blob and with those including Gemini++, a statistical decimation code. When the AC stiffness parameter is 2, there is a noticeable presence of events characterized by high multiplicity of IMF even in the primary case. This could be attributed to soft nature of nuclear matter, which is expected to have a greater propensity for fragmentation. By comparing with experimental data, we obtain the following. The red graph represents AC stiffness equal to 1, while the blue graph represents AC stiffness equal to. The center of mass energy for nucleon as a function of Z for experimental data, red curve, and for the simulation made by Blob plus Gemini++ in two cases. When there is no variation of excitation energy, blue curve, and when a variation is applied, the green curve is shown in the following graph. We observe a plateau in the experimental data in red around 2 MeV for nucleon, while the simulation underestimates this at about 1 MeV. The anomalous points are likely due to events with larger impact parameters than those simulated by Blob. Experimental issues related to time-of-flight calibration may also have played a role. In conclusion, first of all, at 35 MeV for nucleon for MIF major than 3, the charge distribution exhibits behavior typical of multifragmenting sources. These results are in qualitative agreement with prediction of a blob model. Finally, the experimental data are better described by the soft case. Thank you very much for your attention.